Today we're going to be talking about polynomials and evaluating polynomial functions and then the end behavior of different polynomial graphs. So we talked a little bit about polynomials in 6.1. All of your exponents, as a reminder, have to be a whole number, so they're positive. There's no variables up as an exponent. There's no fractions up as an exponent. Your coefficients have to be real numbers. So for instance, it's not a polynomial if you have ix. So no imaginary numbers. Your leading coefficient, once you put it in standard form, meaning your highest degree comes first, your leading coefficient is just what is out in front. The constant is just the number at the end. There are no variables with your constant. And your degree of your polynomial is going to be the degree of your highest term. So for instance, f of x here, our highest degree is x to the fifth. So that's going to go first in standard form. And then you go in decreasing order from there. And because x to the fifth is first, that means that this 3 out in front, leading coefficient. The constant is the number at the end that has no variables with it. So therefore our constant here is -5. And our degree is, when in standard form, the highest degree comes first. So it's x to the fifth, it's the fifth degree. So taking a look at these ones, you want to identify, first of all, if they are polynomials. So looking at this, a couple that are breaking the rules are C. No, because you can have no variables as exponents. Another one breaking the rules is D. No, because you can have no variables in the denominator. And that's also why B is not a polynomial, because you can have no negative exponents. In essence, that would make the variable in the denominator breaking the same rule as B. Therefore, A is a polynomial because it's not breaking any of the rules. So we want to write this in standard form. So the -4x would come first, and then the 2/3 after it, making its degree 1. The type means, since it's a degree of 1, this is a linear polynomial. It's also a binomial because there are 2 terms. The leading coefficient then is going to be -4. If we needed the constant, your constant would be 2/3. Okay, so we can actually take and evaluate functions. You can use direct substitution by taking f of 3 and just plugging 3 in anywhere you see an x. Once you do that, then you just evaluate using your order of operations. So exponents go first, and then you multiply by the number out in front, and then you combine all like terms. There is another option. You could use something called synthetic substitution. To use synthetic substitution, you would put whatever you're plugging in up in the box. You would then do your coefficients, so 2, 0, -8, 5, and -7, again, making sure that I have 0 for placeholders. And you would go through the process of using synthetic division. So multiplying things back up and then adding down. And when you do that, you would get 98 as your remainder. So whatever your remainder is, would be what f of whatever you plugged in is. So that's called synthetic substitution. You tend to work sometimes with smaller numbers if you do it that way, but you can honestly do this problem either way. Okay, so for this next one, we're going to go ahead and take and find f of -4. You can plug it in directly if you would like, or you could go ahead and use synthetic substitution. Doesn't matter. Either way, you'll get the same answer. So we're going to go ahead and simplify. So 2 times -64 is -128 minus 16 minus 20 plus 4. So f of -4 in this case is -160. So with polynomials, you can plug in values and get values back out, but you also plug in expressions and get expressions back out. So looking at this, we have 2 different things we want to evaluate. We want to evaluate g of 5a minus 2, and we also want to evaluate g of 2a. So I'll go ahead and do g of 2a first. I'm going to put that right here. So in order to do g of 2a, you're going to plug in 2a for x. And so you're going to plug 2a in for x, and you're going to get 4a squared minus 10a plus 8. Okay? Then what we're going to do is we're going to do g of 5a minus 2 by plugging in 5a minus 2 in for x. And then we are going to simplify from there. So this would be 25a squared minus 20a plus 4 minus 25a plus 10 plus 8, which when you combine like terms gives you 25a squared minus 45a and then plus 22. So now what we're going to do is we're going to go back and say, okay, I did each of those parts. Now I'm going to put it together in the way the problem asks me to. So I'm going to do 25a squared minus 45a plus 22. I'm going to add 3 times 4a squared minus 10a plus 8. So when I do that and combine all of my like terms, I'm going to get 37a squared minus 75a. 24 and 22 would make 46 in total. This would be my final answer, putting all of that together. Okay? So what I would like you to do is pause it, and now it's your turn. You try this next one, take a moment and try it, and then come back to the video. Okay, so let's see how this one went. So you can see each of the parts plugging in the negative 4d plus 3 and then h of d. And then you can see combining them should give us 31d squared minus 141 over 2d plus 69 over 2, or you can see the decimal equivalent to that. So that's the first half of this is all kind of talking about things we can do with polynomials. The second half, we're going to move to graphs of polynomial functions. So some of these are going to be familiar to you, some of these are going to be new to you. So if the degree is 0, you have something that looks like f of x equals 2 or y equals 2. This is called a constant. And if you were to graph y equals 2, think about the graph. That would be just a horizontal line. It's a constant line there. Whereas this next one, you have something that looks like this. You're familiar with this. This is linear functions. You had a lot of Algebra 1 dedicated specifically to linear functions. Now, if you were to go ahead and graph this, you could graph it in slope-intercept form. Your graph should be a line. The next one, you can tell the highest degree is 2. That is a quadratic function, and we have been studying that a lot. So your graph of quadratic functions are going to be a parabola, either opening up or opening down. And that's the extent to which we have studied so far. So we're going to actually open the door here to new types of functions. You are going to have something like x cubed. This is new. This is a cubic function because your highest degree is 3. When you graph cubic functions, your graphs are going to look something like this. Okay, that's kind of a new one for us. It's kind of like a quadratic function, but doubled, and like one goes up, one goes down, and they're connected. The next one is going to be if you have something that's like x to the 4th, your highest degree is 4, and so that's going to be quartic functions. Now, quartic functions are going to look something like this. So you're going to have kind of like a couple of parabolas put together, but they're both going to end the same direction here, where we're going to both be pointing up. Okay, so quartic functions look something like that. The number of maximums and minimums is going to change based off of all of the stuff that goes with the quartic function. The last one here is anything to the 5th degree. So looking at that one, that's going to be a quintic polynomial. Your quintic polynomials are going to look something like this, or potentially something like this, Again, it's all going to be dependent on whatever goes with the fifth degree, but your graph should look something like this, where you notice one end points down and one end points up. For naming polynomials, you don't just have x to the fifth as your highest degree. They keep going, so there's 6 and more. So anything that's 6th degree or higher, we're just going to call it the nth degree. So for instance, if you have x to the 8th, we would just call that the 8th degree polynomial. So now what we're going to do is we are going to be looking at the end behavior of your graph. So the end behavior means what's happening to the right and what's happening to the left. So that's kind of what we are looking at on our graph. So where it's going on the right and where it's going on the left. So here is your notation. You're going to be able to need to know what this means as you look at it. This stands for, as you go to the right side of the graph, where is your graph going? And then as you go on the left side of the graph, where is your graph going? So the way you know it's going to the right is the x is going to positive infinity. This means as you go to the right. Whereas this next one, you can see x is going to negative infinity. That means on the left of your graph. Then the f of x is sometimes written as y, but the f of x is saying, where is your graph going? So on the right side of the graph, you can see that I am pointing upward. Upward means that is positive infinity. And the next one on the left of my graph, you can see that I am also pointing upward. Pointing upward still means positive infinity. So this is saying as I go to the right, my graph is going up, and as I go to the left, my graph is going up. The end behavior is going to be based off of two things for polynomials. So looking at all of these, notice they all have even degrees. Also notice that in front here is a positive leading coefficient. So with quadratics, you look at that and you say, hey, I know that's going to be pointing upward and it's going to be a U shape. The new part here is that x to the fourth is also going to be pointing the same direction and it's going to be upwards. And the same thing with x to the sixth. It's going to be a U-ish shape. There's going to be some number of curves, but what's happening is it's going to be pointing the same direction with both ends, and it's going to be up because your leading coefficient is up. So for all of these, on the right of the graph, you'll notice all of these are pointing upwards, and on the left of the graph, you'll notice they're all also pointing upwards. Whereas this next one, notice it's the same idea. They're all even degrees. So with all of these, you notice both of the graphs, or all of the graphs, are all pointing downwards. And that's because the negative leading coefficient means it's going to open downward. And think about your quadratics. You're used to seeing that. If your a value is negative, you take your parabola and you flip it upside down. Well, now everything that has an even degree is going to follow that same pattern. It's just they're going to have different numbers of curves in between, ending down on both ends. So this is saying on the right side of the graph, where is your graph pointing? And so on the right of all of these, they're pointing down forever, which is negative infinity. And the next part is saying on the left side, all of these are pointing down as well. They're both going the same direction. That's going to be different for odd degrees. If it's an odd degree with a positive number out in front, so x, x cubed, x to the fifth, all positives, if you're looking at the right side of your graph, those are all going to be pointing upwards. If you're looking at the left side of the graph, they're all pointing downward. And again, they have different number of curves in between, but think of it like a positive slope. It starts low and ends high, and for these ones, you'll have some number of curves in between. Let's take a look at this last one then. With the negative leading coefficient, think of a negative slope. For all of these, you are ending on the right side down, but on the left side, you are pointing up.